People are beginning to file in. This is going to be a great webinar. Airtightness is such an important topic, Andy, so it'll be good to hear. Yeah.
Some of this is going to be old news. Some might be new news.
Yeah, exactly. Well, it was interesting that it tied in nicely with the carbon conversation we were having earlier in our earlier webinar today. So
yeah, it sure did. Sure did.
So just wait for a few more people to file in here. And then we'll get started.
Mr. Corey McBurney is there.
Oh, good. Hi, Corey.
Good to have you.
All right. Okay. So I'll share the results from the attendees that have joined us so far. And then I'll have one more poll for you, then we'll get started. So once again, we're coast to coast, and we have quite a few Ontario folks with us today. So thank you for answering that poll. Got one more here. Just want to know what your occupation is. Let us know here what best suits your occupation. If it's not listed, then just let us know in the chat.
Oh, that's a nice mix.
Mm-hmm.
The advisors, architects, engineers, builders.
I'm not going to lie, I always love seeing it when the renovator trades contractors category has someone in there too. So
there you go.
So thank you to that person from the renovation trades and contracting industry. Puts a smile on my face. All right, so I'll just share that. Looks like we got a few people that don't fall into these categories, so they'll let us know in the chat. So I'll just share this. There you go. So yeah, nice mix. Right across the board. All right. Okay. So thank you everyone for participating in those two polls. My name is Stephanie Coleman. I work with Building Knowledge Canada. And today we are joined by Andy from Building Knowledge, and he will be speaking about the all important topic of airtightness. Of course, we have a webinar series that we actually just had our third out of the 4-part series this morning. And the fourth one will be next week, but this is a 4-part carbon series that we have been running for the month of November. All of it is available on our website. As the recordings are posted, we add them to our website. So you can go back and watch any of those ones that you may have missed. And I wanted to let you know that next week is the builder panel, and the 3 builders that will be participating in next week's carbon webinar are Doug from Doug Terry Homes, Roya from Minto, and Philip from Mattamy. So we're really excited to have those 3 builders join Chris and myself for the 4th and final webinar in that particular series. And of course, these webinars are made possible by our friends at Enbridge. And so we want to, of course, extend our thanks to them for their continued support of the building industry in getting out this critical educational information that we all need to hear. So Andy, I am actually just going to hand it off to you. I will make one comment though, just so everybody knows, this is being recorded, as I mentioned, and it will be sent out to everyone in an email with some resources, and then it can also be found on our website. And any questions that you have for Andy, just put them in the Q&A function down at the bottom there, and I will ask him as we go through the session. And for chat, just use that for kind of general comments, and then that way your questions don't get lost in the feed. All right. Okay, Andy, you're up.
Awesome. Thank you, Stephanie. Yeah, so welcome everybody. And like Steph said, as you have questions or conversational pieces, put them in the chat or in the Q&A. And Steph's going to stop every once in a while if we get lots of questions, or if we don't, we'll go to the end and then we'll try to dialogue some. So the presentation today is sort of a nuts and bolts presentation on airtightness. Now, I will say it's, what do we have? An hour. Air Quality actually has a really nice full day air barrier training session, which we get into, air change versus normalized leakage area, NLR, NLA, and all those little detailed nuances. Whereas today, we're more of a high level building science. Why is it a concern to us? and why is it more important than it's ever been before? So my name's Andy, been with Building Knowledge for a number of years, and glad to work with folks like Stephanie and Angela and Rob and Gord and the team. So today we're going to talk a little bit of history about airtightness. We're going to talk a little bit about code. We're going to get into the science, and then we're going to talk about why is this an issue? And the reason this is important, and actually one of the reasons why we have chosen to put this on and Enbridge is helping us with this, is because there is a national debate going on, whether you know it or not, as to whether air tightness should be mandatory or not in Canada for residential homes. South of the border, it's moving ahead. Up here, we seem the direction anyways by provinces, territories, CCBFC to Codes Canada was air tightness shouldn't be mandatory. So hopefully when you leave here today, and again, this is just my opinion, Billy No's opinion, hopefully you understand why that single decision may actually result in some very significant issues for our homeowners in Canada. Air tightness is about a whole lot more than just making an energy efficient home. And sometimes we have to remember why we're actually doing this stuff to really understand why it's so important. So back in the day, actually, Canadians held the responsibility of developing the blower door test. Harold Orr, one of the only builders to win the Order of Canada here about 3 to 4 years ago, the original designer and constructor of the Saskatchewan home, the early developer of the R2000 program. This gentleman is held in high esteem by Passive House. The developers and founders of Passive House Germany also looked to Harold Orr and the Saskatchewan home as sort of being the foundational to the development of their program and specifics. We have blower doors these days, but who knew that back in the day, the first blower door was developed by Harold and team? And the way Harold tells this is, you know, when they were trying to figure out what infiltration was in a home, they were using dissolving chemicals and measuring the dissolution time in the home to sort of calculate what the infiltration rates were. But how would you do that in a home that was occupied, or how would you do it cost effectively? So they went out and developed this little kit. In fact, if I remember the story right, Harold said they actually got a little blower motor from Princess Auto and put this thing together and developed some of the first blower door technologies through work that the NRC here in Canada did. And to Harold's point, really, before that, it was just sort of a guess. We do know that there are air tightness metrics, you know, the good old days, the R2000 program, even till today, the benchmark for a home was 1.5 ACH. We have, you know, Passive House, which sort of had its establishment in the 1990s of 0.6. We have Energy Star, again, at around that 2.5 as a pass-fail minimum. And we have, believe it or not, the IECC. Those of you that are not familiar with what the IECC is here, the IECC stands for the International Energy Conservation Code, which is in fact the energy efficiency code for homes in the US. And in zones 1 and 2, believe it or not, it has been code since 2012, zones 1, 2, actually all zones, to have an air tightness of, let's say, between 3 air change and 5 air change. So long history in this, and these things continue to progress. Here in Canada, we know that we're trending, especially in Ontario and the other provinces, trending towards this proposed tiered energy code, this 2020 tiered energy code. You know, it looks like it might be, you know, 18 to 22 months, according to the Ministry of Municipal Affairs and Housing, from the time that it's published, that we might see the adoption. But the point we want to make here is that at the end of the scale, up here around net zero ready, which is sort of tier 4 to tier 5, sort of in the middle, is that you are going to be looking at minimum 2 air change for attached buildings and a 1.5 year detached. Now, like I said, it's not going to be mandatory. But let's be truthful. When you look at energy modeling, when you look at impact on the enclosure, when you look at impact on durability and on the homeowners, air tightness is going to be the single most cost-effective, low-hanging fruit way to deliver more efficient homes as we move up these tiers. Folks out in British Columbia, obviously, they have their own code. It's called a STEP code. It is very different than the tiered energy code. Some will say it's the same. It's not. It is very different. But again, one of the main differences there that British Columbia did is they actually made airtightness as a requirement, period. There is no option. And part of the reason it's interesting to talk to BC Housing, Wim Lung and some of these other professionals out there that participated, Zachary May, that participated in the development of the BC STEP code. And they will tell you that airtightness, the reason they made it mandatory wasn't just because of the energy efficiency. Yes, it was important, but the reason they did it was because they wanted the homes to be durable. And we'll talk about why that was so important. So in the National Building Code of Canada 2015, there is that requirement to have an air barrier. And the point we want to bring to your attention is the reason air barriers are in our building code, principally, first and foremost, really has nothing to do with energy efficiency. In fact, the reason that you want to keep a home from having continuous air leakage is to provide protection, to prevent excessive moisture condensation in the spaces during the winter. Folks, we live in Canada, and the issue we have with air leakage is that 3/4 of the year, the air inside of the home is wanting to exfiltrate to the air at the outside of the home throughout the roof area and the balance of the above grade structure. And when it exfiltrates, it carries moist air. This is why we have air barriers in the building code. The reason it was put in the 1990s was because we saw insulated homes that had poor air barriers get completely destroyed. And I'm going to share a couple pictures with you that'll sort of remind us why in the world we did this in the first place. So the residential code in the US, just a little update, they do have a 2021 IECC. There is a 2012 through 2021. Every state adopts whichever version they want. Some are behind, some are ahead. But I do think it's important to note that the states that have adopted between the 2012 and the 2018, which are 27 US states, including states like the state of Michigan, the state of Texas, they require blower door testing as a code compliance metric. And again, it wasn't just to prove the energy efficiency, it was to secure a safely constructed envelope that wouldn't have problems because of interstitial condensation. So this is what happened. The building science was, when we add more insulation, we make the envelope colder. And what that means is you have less drying potential and you have more colder surfaces in the enclosure, and you're immediately at the risk. What does this look like? Well, for those of you that have torn houses apart, Stephanie's a renovator. Myself, renovated a number of homes, even a lot of service on new homes as a new home builder. We have seen some of these things and we continue to see them. This looks really bad. The black stuff, the decay behind an outlet where the air leaked and it got wet. It got wet enough for long enough that decay was made. Roof sheathing, decaying, wrinkling, falling apart because of air leakage, not improper venting, not for the lack of insulation, but because of poor air tightness and moist air leaking into the attics and condensing on the bottom. And then to the left, extreme cases where air leakage caused so much condensation in the envelope that it actually was near to the point of causing some structural failure. So again, we need to remember why we do this. This is sort of interesting. If we think about the building science, we know that outside it's going to get very cold. On the inside, it's going to remain warmer. For those of us that are Canadians, like, who do they say? We only have 2 seasons, which is this winter and next winter. But for most of the time, it's warmer with more moisture on the inside. As the air leaks from the home, just draw this a little bit, into a hole, it leaks into the wall. And as it crosses the insulation, it becomes colder and colder. Now, that moist air does not condense inside of the insulation. It doesn't condense until it hits what's called the point of nucleation, or the first solid cold condensing surface, which is quite frankly the very back of the structural sheathing, whether it's plywood or OSB. When it does it, it turns to moisture. Now, for part of the year, it's going to turn into frost, not a problem. Here's the issue. Sun comes out on a winter's day. It's behind a red brick wall. It's not going to turn to frost. It's going to turn to water. And if the rate of wetting exceeds the rate of drying, we are going to have problems. Yes, OSB and plywood can open the cell structure as it gets wet, and they allow some drying potential to happen. They're like natural smart vapor barriers. However, what happens is when the rate of wetting exceeds the rate of drying, the plywood and the OSB cannot dry fast enough. So here's a sample. Here's a wall built in zone 5. We're looking at a house that has, what do we got here? 20% relative humidity. It's inside the home. It's 21 degrees C. And what we're showing here is that at about the time frame of November, the backside of the sheeting becomes cold enough and the wall cavity becomes cold enough that any little portion of air that gets into a wall, and we know that it will because we don't build submarines, you have a potential risk of condensation, and the risk gets deeper and longer as the winter goes. And that's a home that's 20% RH. Folks, I don't know about you, but 20% RH or lower, you're shocking the cat, you're getting sparks on your fingers, your mucous membranes are drying out, you're starting to get sick. It's not a real healthy condition for us to maintain homes at that low of range. But what happens if we raise the humidity in the home? So let's put it to 40%, which is really, some would argue, almost too high. Safe range is about 35, but let's put it to 40. See the difference from here to here? That is a significantly different amount of condensation risk just because the homeowner has chosen to put the relative humidity a little bit higher. So again, the building code reasons of why we need airtightness targets, why we need air barrier details is number one, to keep the walls dry. The other thing too is keep in mind, water is what destroys walls. The number one water mechanism, damage function, is rainwater, exterior liquid water. The second is actually air leakage. And so by doing these things, you make the homes last longer. And we do know that homes built according to the National Building Code of Canada should last 50 years. The other thing too that's important to understand is that the other part of airtightness, and this sort of goes against this social commentary that you can't make a house too tight. We've even heard people in brown overalls and clean white shirts on television shows say, this airtight home created terrible indoor air quality issues. The reality is, and Canadians have known this for years, that have studied this, is that airtight homes with proper ventilation have the best indoor air quality of any homes. Studies were done on our 2000 programs. There was CMHC studies done to quantify this. And here's the general theory behind it. You cannot control a sieve. When you make a home airtight, you are giving the homeowner the ability to use the systems of the home to control their indoor air quality. If you give them a sieve with holes, good luck trying to help them solve their indoor air quality issues. And of course, there's the other notional concerns about energy reduction and obviously environmental impacts, wasting resources and so on. So the National Building Code of Canada, just to reiterate the point, if you want to know where that is, the explanatory piece is in the appendix 5.41. It's also the same as the Ontario Building Code as well, as to why we have air barriers, and is to limit interstitial condensation. Back in 1990, when we finally figured out, coming to the conclusion of why our walls were getting wet, we finally detailed continuous air barriers. There was a lot of work that was done. This is from an old ONWHIP. For those of you who remember the Ontario New Home Warranty Program or HUDAC, these were some of the requirements. And along with air barrier systems came the ventilation requirements. So when we started to put air barriers in, Canadians were really smart and said, hey, we're going to have continuous air barriers. Let's make sure we have ventilation. So they put in ventilation. HRVs and ERVs were proposed to go into the code, but it didn't develop at the time. And instead we went with exhaust only. So in other words, you turn the switch on for a bathroom fan and it sucks air in the home through the holes. Problem with that is, how many holes do you know you have? And does that mean if you want good ventilation, you put more holes in the house? So now today we know that balanced ventilation with an HRV and an ERV is the best match for airtight homes as we build them today. So let's talk a little bit about the math. How does blower door testing get figured into the energy calculation? So here is a simple picture of what a blower door does look like on the home. You'll notice that it has air. The blower door actually depressurizes the home. You can run a test pressurizing the home as well, but specifically most tests today are run depressurizing the home. And what it's meant to do is to simulate the as operated conditions the home is going to experience when the homeowner moves in. So by doing that, we can compare air tightness levels of homes, and we can use some of the blower door test results to predict the energy impact or predict how the home is going to operate under normal circumstances and scenarios. So what happens is, this is a copy of a blower door test result. And what you're seeing here is you are seeing a series of tests done. So this is a test that was done on a home. And what you have here is the blower door test starts out at about, you're supposed to run it, you're supposed to hit at least 50 pascals, which is sort of the design pressure. In this case, we ran it a little bit higher, but it has 1, 2, 3, 4, 5, 6 test points, minimum 5 to get a proper test. At each one of these settings, as the door is running, it takes 100 readings and it plots it on a line. And then what happens next is it extrapolates some of these details as the blower door test is running. So here we know, for instance, that the CFM blower door is a simple mathematical equation that takes the fan pressure, or those 50 Pascal pressure differences, times a multiplier. And this is how we get the ACH, is it's the CFM that is read, the amount of air that is being allowed to be extracted when the home is at a 50 Pascal pressure difference times 60 divided by the volume of the building gives you your air change at 50. So it's a volume-based calculation, and that's how the ACH at 50 is arrived at. So how do we extrapolate this? Because we know that when we're testing homes at 50 Pascal pressure difference, it's equivalent to a 35, 45 kilometer-an-hour wind blowing on all sides of the home at the same time. We know that we do get pretty extreme conditions, but how does that help us make judgments about how the house is leaking under normal conditions, daily conditions? So in Canada, based on a number of years of science, Canada is actually based on the Alberta infiltration methodology, the AIM principle, that we came to understand that if we actually if we're able to take the slope of the line and bring it down to the point here where we are at approximately the intersection of the 10 Pascal pressure difference. So by looking at where the slope is at 10 Pascals, which is assumed to be the average pressure difference over the course of the year, we then can look at what the CFM is at under normal conditions under that range. So that's how some of the extrapolation is done to take the blower door test results and apply them to the energy calculation. Again, if you want to dive into the details, here's actually the math and the system assumptions behind it, the flow rate embedded within some of the calculations in the software or the blower door test results. It is looking, the Alberta infiltration methodology does look, number one, at the stack coefficient. In other words, as the home height increases, as you add floors above grade, so does the stack coefficient. So the higher, the taller the structure, the more pressure there is at the top. And what it does in the calculations is it actually assigns higher leakage to the higher levels of the home. So you'll actually see homes that are taller actually be more affected by air leakage than homes that are a single story with just a slab on grade or a basement. And that just reflects the science. We know that as you add 1, 2, 3, 4 stories onto a home or a building, you add about, I think it's in the range of 3 to 5 Pascal pressure addition with every floor. That means that warm, moist air in the winter is going to be pushing even harder on the topper levels of those buildings, the taller it gets. And then, of course, the thing that also increases the air leakage and the pressure difference is how cold it is outside. So the colder it is, the bigger the pressure difference between the inside and the outside, the stronger the force is driving to push that air to the outside of the home. And again, so if you look at these results, this comes out of a blower door test simple sample result that we would get in the field, again, running the TechTight software from Minneapolis Blower Door. And you'll see here that this test was done on the home, the volume of the home, the air surface or the surface area of the home was input, the condition of the home, the current temperature on the outside and on the inside was considered. The location of the home was all put in. And you'll see that as a result of running the test, that this home was measured to have 4.11 ACH at 50 pascals. So what that equates to when you look at the equivalent leakage area at 10 pascals, which will then be used for the energy consumption variables, it's assuming an equivalent leakage area of 158 square inches. In other words, that's the equivalent size of all the holes added up and the amount of air that will flow in and out of them at a pressure difference of 10. The other thing too that comes into play when we look at the air test results is there are details in the building leakage curve. In other words, the slope of the line that can tell us characteristics of the house. In other words, there's more to blower door testing in the results than just the ACH. We can actually start to tell, depending on the slope of the line, the N, as to whether the holes are large or whether they're small. So if some of you remember back in school, you learned about a little bit about fluid dynamics, maybe some of you that are engineers or architects or construction engineer technologists. As fluid flows through a hole, there is a coefficient. One is a coefficient for a smooth edge orifice, which would be indicative of large holes. And then there's a coefficient for a sharp edged orifice, which would be indicative of a small hole. Small holes meaning that there is more resistance. The larger holes meaning that there is less resistance. So typically if we have, let's say, an N from our blower door testing results of 0.8, we're going to start to assume that, hey, the holes in this house are really smaller holes that add up. Whereas if we start to get up over 6.54 or so on, that we start to see that there's less resistance, which means there's likely a bigger hole someplace. And those big holes are really the ones that we're mostly concerned with when it comes to condensation in interstitial spaces. And this is why it's sort of good to know that there's a difference. Here's an interesting scenario. In this scenario, we're actually showing you a blower test result that gave us essentially on two homes the same result, 1.82. So from an energy advising standpoint and everything else, it would seem to be okay. However, there are some nuances in this. Look at the difference in equivalent leakage area. All of a sudden, we actually have this home to the left has a coefficient of 0.8. And what this is telling us is that actually at 10 Pascal pressure difference, we have 250 CFM of assumed leakage. Whereas the house over here that seems to be the same actually has larger holes, 0.54, And in this house at 10, it's almost twice as much at 400 CFM. So again, we're more concerned about the home on the right than we are on the left, even though from an energy perspective, you may just look at both as being the same. So these are some of the factors that our team at Building Knowledge looks at. It's what building science teams look at when you're actually looking for durability factors with the envelope and in the projects that you're working on. Get my mouse set up here. So yeah, 260 to 400, it's a big difference. And again, just a difference in the size of holes for basically the same home. So again, the question you have to ask is the impact on energy use predictions. And again, the slope, what is the appropriate slope? Like what should we be looking for on these projects? And we would say, for all practical purposes, we like to see ports sort of in the range of that 0.65. So again, what this is saying, if we take that same home, that 2,300 square foot home, and we have a slope of 0.8, let's pretend that the air is 20% relative humidity, pretty dry in the wintertime. And let's actually assume a 5 Pascal pressure difference, so less than 10, so even a more limited. And you start to look at the overall calculations. What you're going to have here is you're going to have about 150 to 75 CFM, sort of 150 CFM, 75 leaking in, 75 leaking out. So you've got 75 CFM. Again, you do the calculations. You add to it how many cubic feet of air a day that 75 CFM is going to bring in. Then you do the translation of if you have 75 CFM and you have air inside that is at 20% relative humidity at a given temperature, we take the moisture content of that air, that's that 13.5 times 21 grams. We know that under the 75 CFM exfiltration numbers, that there's 24 pounds of water or 11 liters of water per day moving through all of the holes, the combination of holes in that home. If you move that home to 40% relative humidity, it doubles it to 22 liters per day. So again, this is why the math behind the blower door test really matters, and probably why we should be looking at some of these numbers more than just ACH. Again, I'll just go back to the scenario we showed you. It's that difference that when you start to add and you start to play around with leakage, the size of the holes, the leakage coefficient, and you start to consider the interior condition, you can start to see why holes in cold climates matter in keeping building enclosures durable. So again, question is how tight do we want these homes to be? Yes, it does change when we add more insulation. And again, when we increase indoor relative humidity or we put in better windows, it does have an effect on these walls that we're building. The second thing that's important about blower door testing or air tightness testing is the impact that it has on the sizing of the mechanical systems. So to your left, you take a simple single detached home, again, the same 2,300 square foot home. It has a blower door test of, let's say, 3.5. We know that's high compared to code, but let's just take the average home. It is interesting to note that the air leakage contribution to the total heat loss is basically more than anything else in the home. Windows are at 20, foundation 25, walls are at 20, and attic, again, probably down around 5%. So what happens is if you have an ACH of 3.5, HOT 2000, you do the energy model, it's going to put the home at 116 gigajoules a day. If you're able to decrease that home from 3.5 ACH to 1.5 ACH, you have a decrease of almost 12 gigajoules. That's pretty impactful. How do you apply this? Well, here's what happens. If you have a home, again, that was built back in 1997, would have had a 86,000. Today's homes might have 41,000 heat loss. Net zero homes, again, because of the reduced air leakage, you'll be down around 27. So it all seems pretty positive that when we can apply the actual air tightness, we can see a significant decrease. Where does this happen in the heat loss, heat gain calculations? It happens within what is called the envelope air leakage calculation, or the infiltration calculation tool in the CSA F280. And in the CSA F280 standard, they have several embedded spreadsheets, one of which is this envelope air leakage calculation tool. So in this embedded spreadsheet, the building designer, the mechanical designer, has the ability to actually enter the proposed air tightness of the home. They can either choose from a selection of drop downs of energy tight, which would be approximately 1.5. A code built home is, I think, 3.57. Or they can put in what's called custom blower door test data. So if you know that you're going to do Energy Star, you know that your pass fail is 2.5. So again, you can put in the 2.5 in the equivalent leakage area. If you're doing net zero, single detached, you know that your pass fail is going to be 1.5 or 2. So again, you can put that information in there. And what it does is it then shows the resulting reduction or the impact on the heat load and on the heat gain both. What's the difference? Well, in some cases, it's pretty significant. We've seen cases in zones 4 and 5, so that's anywhere between Victoria, Vancouver to, say, the Toronto area, sort of a zone 5. So I'm going to say I would argue the least impactful areas, the warmer climates of Canada, because this gets even more exaggerated as you go north. But in zone 4-5, 2-story, single detached home, typical home, 15,000 volume, a 55 degree delta T temperature difference. So let's say you're at 22. So this would run down to minus 25 to minus 30. So a loose home, an old home at 10 ACH, is a difference of 12,000 BTUs. If you're able to get it as tight as a code home, it diminishes the air tightness impact down to 4,000. And again, if you're able to get down to that energy efficient range, we would say you're down into 1,800 BTUs contributed to air infiltration. The other thing is, let's look at its context versus other measures in the home and the building. Now, what I'm not saying is you're going to do air tightness and you're not going to do insulation. That's not the point. The reality is this is simply to help prioritize. So on that same home we looked at, 3.5, going from a 3.5 air change to a 1.5, which is a good change. It's from basically a simple standard code maybe to about a net zero ready in air tightness, is an 11 gigajoule energy reduction. Now, in the same home, if you were to add 2 inches of insulation, that would only be 5 to 6 gigajoules. Now, 5 to 6 gigajoules is nothing to sneeze at, folks. 5 to 6 gigajoules is about $10,000 to $15,000 worth of solar on a home. So for instance, 3 to 5 air change down to 1.5 is 11 gigajoules. Well, guess what? 11 gigajoules, it comes out to about 3 to 4 kilowatts. So you're looking at a pretty substantial cost offset if you were going to try to generate as opposed save with air tightness. The air barrier too, the other thing too that we are seeing change, and our recommendation to the industry is, if you haven't got around to looking at exterior air barrier opportunities or other things other than poly, caulk, and tape and foam, you need to do it now. We are in the midst of a trade crisis. We're finding it very difficult to find materials, to find trades, and an interior air barrier using polyethylene and caulk has to cover 45 to 50 different types of details and intersections. Whereas an exterior air barrier, a house wrap, or a certified exterior foam as an exterior air barrier with its proper approved taping only has about 20 to 22 different scenarios that it has to seal. So again, the other thing too is you can start to look at a variety of materials being the air barrier as opposed to just one. So traditional would be poly, caulk, tape, you name it. And exterior would be something like a foam with a proper seal, like the Codebird air barrier systems. Here you see the Tyvek DuPont system applied as a air barrier again, we are moving to the exterior. Sometimes we get asked, our team gets asked, because we have the privilege, I'm not blowing our horn, but we have the privilege of working with some really good builders that get really good air tightness. And I'm not just talking about the builders that do 1 or 2 a year that hit that 0.1 or 3 times less than passive. I'm talking about some very conscientious, good quality builders that are even large scale production, builders that on a daily basis hit 2.5 to 1.5 on a regular basis. And we get asked, how do the builders do it? And I'll tell you, one of the ways they do it is they do it early. In other words, they're looking at air barrier detailing before the details ever go to the field. They're able to take a red line and draw it through the drawing where they can see the connection of the air barrier. I'll give you another tongue-in-cheek piece of advice. They also have drawings that purposefully identify the air barrier as opposed to calling it a vapor barrier / air barrier. Folks, let's identify the air barrier separately, give it its proper detail, and then notionally reference the vapor barrier if and only when that's actually what it's doing. We really need to get away from calling it the vapor barrier in industry and understanding that that is something entirely different, and that the thing we're really concerned about is air barrier. So again, just my opinion. So get it into your scopes of work, get it into your drawings. The framer can then use it. You can train to it. There is no question. The insulator can use it. It's now in your scopes. Your drywaller, the cladding individuals, the trades that penetrate it now know that it's a detail. I know I supervise thousands of homes myself, and I get it. Many of you are thinking, well, Andy, we're going to do the detailing, they're going to ignore it. I would argue, you know what? Yes, they might. However, you don't have a hope in heck if you don't at least try. So you've got to get the details right, figure it out in the office, figure it out with the teams, do the training, and then they'll know what to do in the field. And sometimes they might not do it exactly the way you want them to, but if they know simply that you're trying to achieve air tightness, they might at least come up with even a better detail than what you have. So everybody needs to know how to deal with it. Historically, again, these interior air barriers, we tend to do a lot of things. And you know what? Sometimes it's just all these beads of acoustical caulking. And why do we need them all? The reality is we don't. And if you're going to do it, let's just put the caulking in the right spot. Again, trying to do things here, we sometimes see this, foam, someone's gone along the floor and thought they were going to seal the gap. Well, number one, it's just a really bad job. Number two is, 2-part can foam does not seal gaps that small. It can't. It can only seal holes that are 1/4 inch or larger, because in order for the foam to actually cure and form its airtight structure, it has to be exposed to air. And when you try to jam it in a hole, it ain't sealing, folks. This is time that's wasted and material that's wasted, whereas it could be better use. So let's talk about the why. So what happens after you leave the home and maybe miss a couple of these things, some of these standard details? So here's part of the thing. Here's a plumbing stack running up a bathroom wall into the attic. Not sure what they intended with the red tape, but that is not a good way to seal the hole. We need to do that better. We need to possibly try to use either some can foam or even some caulking if it's a tight cut hole around there, as opposed to that. That said, here's what happens if you don't seal it right. You get the black stuff. You get the premature curling of the shingles that signals to the homeowner that something's wrong. You might replace the shingles. The problem is the real problem is the air that's leaking up from around the unsealed vent stack, condensing on the underside and causing degradation to the roof structure. The other one is this. It's header wrap, very prevalent with an exterior air barrier detail. We put it on, we gift wrap it, we get our framers to do it right, and then we allow our other trade contractors to come in and have no clue as to why the material was even made. And how important is it? Well, if you get the header wrap wrong or you compromise it, and even if you don't seal it correctly, Here on the floor, there's no caulking and sealing. The result you get is this. What you're seeing up to the left is when the blower door test is running, is you are seeing cold air leaking to the inside of the home. In this picture, what was happening was there was so much air leakage through the non-wrapped or poorly wrapped air barrier header detail that there was condensation forming on the floor during cold periods of this home and making the tile slippery. When you have exceptional air leakage through a header, you can get worst case scenario, high levels of degradation at the holes. Another area that we often see gets forgotten is the simple measure of caulking at the top plates. And here's the problem with that. If there was ever an area where you are going to get a lot of pressure difference, in other words, it's cold outside, that air is pushing at the top part of the home, and it's going to want to push out those holes. And when it goes into the attic, it's going to do some nasty stuff to your attic. So again, there's no caulking, which means there's no way it's going to clamp and seal that air barrier. You'll see here that as a result, when you run the blower door test to the right, you will see that when the door is depressurizing the home, the cold air is coming from the attic back into the wall. All right, maybe that's not a problem. The problem is the blower door test is not telling you what's actually happening. What's happening is the warm air is going the other way. It's going from the wall cavity up into the attic and condensing underside the roof sheathing and causing all sorts of nice stuff like what you have on the left. This is also the leading cause, the lack of this detail right here and penetrations into the attic is the leading cause of attic rain. And that's something that we have been experiencing across Canada over the last several years as we have started to there's areas where building codes require zero lot line, for spatial and fire separation between houses. The fire code of the local authority will tell you have to put non-vented soffits in there. Add to that we're not doing a great job with our air barrier. Add to that we now make the attics colder because we have lots of insulation up there, and it's the perfect storm for having really bad cases of attic rain in our homes. So again, here's the other thing that happens when you don't get the sealing at the top plates right. The homeowner has a dryer or they have a exhaust device like a central vac. Guess what happens? When they turn it on, all that air comes down inside the assembly. I have seen scenarios where there is enough depressurization from a central vac and a dryer that it's pulling hot, humid air down into the wall up against the backside of cold poly, because remember, it was summertime, and it's enough to cause condensation at the backside of the poly, because now we're simulating conditions that we're going to see somewhere down in Texas on a leaky home. And again, no matter what the material is, you still got to be careful of the detailing. Not to say that spray foams are a bad product, but again, you still have to watch that you install them correctly so that you don't get gaps and cracks and separation showing in the assembly. The other part of where, ACH and blower door testing, why ACH is not the end all be all, is when it comes to multifamily units. We are finding that there is a huge issue in attached homes across Canada and the US. You can ask an energy advisor anywhere in Canada and the US today. In fact, our team did a study several years ago where on multifamilies, we actually started to, when we were depressurizing units, we started to look at the effect on pressures on the neighboring units. And any one of these folks in the field, energy advisors, will tell you that when you depressurize a townhome or a multifamily building, that the average amount of air that's coming from the unit next door as opposed to outside air is 30% of it, 30 to 40 is coming through the common wall. So in particular, 1 hour firewalls are incredibly leaky. And again, the building codes today in Canada do not address the separation between units. There is no such thing in our codes as compartmentalization. We see this term in programs like LEED and in some cases in net zero homes, only because they've realized that there are building science consequences. So you can imagine that today we build really airtight townhome blocks, and the air barrier across the building is very, very tight. However, if the air barrier between the units is not tight, what this means is when one of the residents turns the bathroom fan on, or they turn on the range hood, or the pressure difference changes in the end units because of wind direction, you are now going to suck air from the neighbors as opposed to getting it through the holes of the wall from the outside. So we do see, because of the lack of compartmentalization, an increase in odor and sound contamination moving between units. So what are the details? Well, if you are doing 1 hour walls, which are offset staggered studs, walls that provide a 1 hour fire rating, you want to start to treat them as a exterior wall in terms of an air barrier. Some simple detailing, as you can see here. Again, this is a header wrap that's being used on a common wall assembly. You never would have seen that before, but now we're going to treat that header as if it's an exterior. The air barrier on the inside, instead of not having anything at all, because typically on a 1 hour wall, you typically would just put 2 layers of drywall up. You would call it smoke and sound and flame proof, and away you would go. Well, now we're saying get an air barrier there, just like you do the exterior wall. Why is it Tyvek instead of poly? We would suggest, not that this has been proven, but we would suggest that because those walls are very wet during construction, it's probably not a bad idea that at least one side of a common wall has an air barrier that has a higher permeance than poly. Now, we have not seen any damage when there is poly on both sides. And remember, the wettest part of any wall assembly is always the floor assembly. And that floor assembly in the left picture is not wrapped with poly, it's wrapped with a Tyvek, just like the header assembly on the outside, which is highly permeable. So those pieces, those areas of the home still can dry into the units as well as the cavity space between. So this is just a simple detail. Now, the biggest benefit isn't just the decrease in air tightness, it's also the fact that we're starting to see a decrease because of this in sound and odor transmission, which is pretty cool. This is just a little case study that was done with Aero Barrier, who's been doing a lot of work with Enbridge and some partners across the industry. And you can see here that as, when we started out on this test project, that when we did the blower door test without any compartmentalization, these units were coming in at 8.9. When we did a little bit of compartmentalization, we were able to drop it in half and actually get down to an NLR, which is below the 0.26, which is sort of the pass fail for Energy Star. But again, that took a lot of work. It can be done, and it took a lot of work. We see products like Aero Barrier now that can actually take non-compartmentalized walls down to 0.3. And if there is the addition of Tyvek or poly in addition air barrier, you can get down to 0.1 or 2 air change. But again, these are solutions we're starting to see on the market. We're starting to see things like Aero Barrier used a lot more. And again, it's not just to get those ACH numbers. It's to ensure that the unit is quiet. It's to ensure that those folks in Unit 3 aren't going to know that the folks in Unit 5 have cooking classes every Wednesday night, or have or smoke a lot of Cuban cigars, right? It's about sound and security and comfort and health. The Aero Barrier product, I'll just leave a couple notes on that. Again, it does seal quite well. It provides good compartmentalization. It's got verified results. Again, you can see here that as the tests are run, as they start the test to the left of the field, as they finish it, you'll see that the air tightness actually gets much better in the homes as the air, it's about a 75% reduction in air tightness when you start to use Aero Barrier. This was actually a project, a multi-family project that started out at 8.6 air change. And they knew that there were issues cross-contamination between suites that they were going to be faced with. They were struggling to meet their energy efficiency requirements. AeroBarrier came in and worked with them and got a 73% reduction in air tightness, getting them down to 2.31. So again, really, you want to understand that there's a lot of impacts on lowering the ACH of having good air barrier details. And again, it's not just ACH alone. Some quantifiable improvements. This was just a scenario we did on a single detached home, 40-foot home. And you'll see that as you move the air tightness from code across, that you can start to see improvements. And just some of the things notionally that we see happen is, in this home, it went from an air tightness of, what was it, code of 3, and got it down to 0.5 or 0.6 down to passive. And with every decrease, there was improvements. So at the end of the day, this home, simply by taking it down to a low level with AeroBarrier or really good air tightness, there was 18 gigajoules saved. So again, that is 18 is half of about 36, which is about that's almost, what is that? $17,000 to $18,000 worth of solar panels to create that same amount of energy over the course of the year. So instead of spending $17,000 to $18,000, how about $1,000 or $2,000 to seal the unit well, I think is the point here. It got it 15%. Air tightness alone got the building to 15 to 20% better than code just on air tightness. There was a reduction of an entire ton of greenhouse gas. So again, we see the home started out at 5.3, and simply by making it tight, we dropped an entire ton. That means that over the lifespan of the home, you have a 50-ton emission reduction in that home. And again, from a fuel perspective, a 24% reduction in the use of natural gas or fuels. So there's a couple ways. Sometimes we get asked about, well, when we're doing air barriers or learning about these things, what are some of the tools we can use? So there's really good energy advisors out there, companies, ourselves, and others that do this. And there's a lot of different ways. So, we would say pre-drywall inspections are probably at the top. How do you make sure you're consistent and catch these details? A pre-drywall. You will be able to tell more by looking at the details than you will by even doing a air leakage test at the end of the day and trying to find the holes. And what I mean by that is the real concerns with air tightness are always the big obvious holes. A lot of our builders have pre-drywall inspection checklist. It takes all of 5 minutes for a site service guy or a supervisor or even the trade contractor as part of their scopes to go through. It's got 20 items on it. They walk through the house, check, check, check. Acoustical sealant continuous at top place, check. Bead of acoustical sealant all the way around the door frame and window frame, check. Acoustical bead, a half-inch up off the floor on the bottom plate, and able to be compressed by drywall, check. All these kinds of things are a quick check and a quick fix to get some really good results. The next way is to do some pre-testing. So before the drywall goes on, you can check the air barrier. So you can do a depressurization test, a low CFM depressurization test, or you can actually do a pressurization test. So flip the blower door around and check the air leakage the other way. Now it's going to change a little bit, right? Because when you are pressurizing the home, things like windows and doors, rather than being pulled against the weather stripping, are now going to be pushed out from the weather stripping. Bath fans as well, the little flappers are going to flap open as opposed to close, so keep that in mind. But for the purposes of finding holes, pressurization is not a bad option to try. And again, if you are going to do it with an interior polyethylene air barrier before pre-drywall, run a low CFM test or a pressurization test. The other one too is the back of your hand. Great, we could have smoke pencils, and we're glad to get folks smoke pencils so they can see where the air is coming in during a blower door test. But the back of your hand, believe it or not, is sensitive down to less than a Pascal. So typically you can feel that little gentle breeze coming in through the holes at the back of your hand. The other one too, which we feel is really ideal is the combination of a blower door along with an infrared camera. And then this is best done when you have, a temperature difference from the inside and the outside of 15 to 20 degrees Celsius. So, if it's 20 degrees inside and it's 0 outside or less, that's an optimal time to see this. And you can run the blower door, you can depressurize the home, and what'll happen is you'll start to see these blue wispy lines coming in where the holes, and that's where you can differentiate between cold air coming in versus just cold areas due to thermal bridging or highly conductive materials. The other thing too that is a way to do this is if you're in the spring or summer and you don't have the delta T temperature differences, one thing you can do is go out early in the morning before the sun comes up on a building when it's been a clear night and the atmosphere has cooled down the building, it's cooled down the surroundings. You'll put the blower door in, you'll do a depressurization, and you're going to have several minutes where there's enough temperature difference that you'll be able to see the difference as it comes in. And the last one, of course, is testing pressurization with smoke machines. It can be done. You put the blower door on, you pressurize the unit, you blow the theatrical smoke in, and you sit outside and you look for the leaks. We do this on multifamily to actually look for areas where compartmentalization needs to be done better. I just caution you, make sure you let the local fire department know before you do this, because the neighbors may call thinking the building is on fire. So summary, that's a little history on blower door testing. It really is about making sure the homes you build actually last. It's also a way to easily meet code, and it gives you an idea that there's a lot of other information available from a blower door test: size of holes, concerns about the amount of moisture that could get in, that types of thing. And then there's lots of possibilities, how you can decrease your mechanical size. You can start to do some cost savings on the home and the building and the energy efficiency requirements. So a lot of opportunities there for you to take part of. Thank you. Stephanie.
Thank you, Andy. That is great. And actually, so we do have a handful of questions so far, and I'm sure more will roll in as we chat, because we got a few minutes. But I wanted to say that I noticed that we've been joined by Mr. Harold Orr. And
Wow.
He's raised his hand. So I'm not sure if he wants to say something, but Harold, if you do want to, if you want us to turn your mic on, just send me a message in the chat and I will, I'll activate your mic. I never know if somebody actually wants to say something on the screen or if they press the button by mistake. So I'll just put that out there. It is, I know, it's great to have him on here. Anyway, so what I'll do is I'll mention a few of the questions, and then Mr. Orr, if you'd like to speak, just let me know and I'll activate your mic. Okay, so the first question, let me just go here. Can you explain the flow coefficient as shown on the blower door test results?
Yes, I can do that. The flow coefficient, I would have to go back in my slide and find that here. I guess what's the question about the flow coefficient?
It looks like that was the question. They were looking for you to explain the flow coefficient. So I guess how it
works. Okay. Yeah. Let me see if I can find that a little bit.
Sure, no problem. That one came in a little while ago, so it was probably around halfway through your deck.
Okay. I'm going to have to find that. Sorry, Steph. I'm having a problem getting back to my slide. I might have to get back. Whoever that is, let me know who it is, and I'll try to get the information to him if I can't get back to my slide here.
Okay, no problem. I know sometimes in Zoom, it takes a while for the slides to come back up. So one question was, why can direct measurements at 10 pascals not be used?
Direct measurements. Well, one of the little reasons, and again, I don't consider myself to be the expert on this because Harold Orr would be the expert on this. One of the reasons we don't do direct measurements at 10 is because that is a very low, I'm going to say very low flow rate or pressure difference. So what happens is we tend to get more consistent rates when we're able to simulate higher pressure differences. And that's why when a blower door test is done, that's why we always try to aim to have at least 1 point reading at 50 on a slope of, and then decreasing by 5 down at least 6 to 8 readings. So the problem is if we just did our pressure rates at a 10 Pascal difference, we could be over, our readings could be off because there's a lot of different pressures that are operating on the home, stack effect, wind, and things like that. So to overcome some of that variability, we run it at a higher rate. That's one of the reasons why. And then we extrapolate from that slope. So.
Okay, thank you. A question that just came in, you mentioned 50 details with interior air barriers, only 20 with exterior air barriers. Can you give us a general list of these? That way we can add them to the checklist.
There you go. So with interior air barriers, polyethylene or any type of material like that, you've got to remember that you've got to get that poly sealed around, let's say, for instance, the backside of an electrical outlet. So now you've got to make it continuous. And you've got to make sure that you've got that poly in behind the landing that your framer is going to attach to an exterior wall. So it's got to be continuous. So those are details that fundamentally, if the air barrier was on the outside, your framer wouldn't have to do that, right? Even the airtight outlets wouldn't have to have an air barrier around them because the air barrier is on the outside of the wall. So when we talk about having less detailing on an interior air barrier versus an exterior, that's sort of what we're getting at. So to your point, your checklist would be different if your air barrier is on the outside versus if it's on the inside. So you might want to have a specific one for both if you use both.
Well, actually, someone did ask because you had mentioned the checklist that we have, and so it sounds like there may be some interest in getting that. So now, one question came in the chat, and it was: is fiberboard as wall sheathing better than plywood or OSB from a building science perspective?
Oh boy. So fiberboard, I think you're talking about, we've seen a lot more of that this year just because of the lack of plywood, the lack of OSB. We used to see fiberboard in the old days. Some would call it 10 test. It was a darker color. I'm hesitant to comment as to whether it's better than or less than other types of materials. I will just say this. Be very careful with products and understand their propensity, their water absorption rate, and their permeability. So for instance, even plywood itself is different than OSB. It actually can absorb, it actually has the ability, it actually has a higher perm rating when it gets wet. The cell structure actually opens up more and lets the water vapor dry through more so than OSB does. So just know your properties well, take a look at them, and ask the manufacturers questions.
Someone wanted to know where they can get access to that CSA F280 calculator, the 2012 calculator.
So the CSA F280 calculator is available in the F280 standard. So it's actually one of the first, it might still be the only, I'm not sure, but it was one of the first CSA standards that actually had embedded calculations in the standard. So you have to go to the CSA website, buy the standard, $150 or so. You can get an electronic copy, and it comes with several embedded spreadsheets. The air infiltration spreadsheet that I showed you was one. There is a below grade calculation spreadsheet, and I think a slab on grade calculation spreadsheet as well too. Notably, this is interesting to note, those calculating spreadsheets are actually extracted or are the same algorithms that are embedded in HOT 2000.
Okay. Now, one person had asked, is the canned foam considered both a complete air barrier as well as a vapor barrier?
That's a good question. The last I checked, the can foam had a permeance level that was commensurate with vapor reduction. To be very frank, the size of holes that it fills, this is my personal opinion from a building science standpoint, I would be far more concerned about its air barrier properties than I ever would about its vapor permeance. Because remember, vapor resistance really is, even if it's not fully vapor resistance, is such a small surface area. Whereas you're more concerned about filling the hole for air resistance purposes. So, but again, check the manufacturer's information. There should be some vapor permeance numbers to some of that material.
Okay, we had a question on N values. And so they say sometimes we get values less than 0.5 and over 1.0. What do you recommend to use? Should we use 0.5 for values less than that? Okay, that's
I'm going. That's a good question, but I'm going to suggest, not knowing the context you're using it for, I'm going to suggest as a registered energy advisor that you actually default to the recommendations that come out of the Interguide rating system blower door testing protocol and the CGSP standard as well too. So I'll default to that.
Okay.
Off the record, we can have a conversation about various scenarios.
Part B of that question was regarding extrapolating the blower door test data down to 10 pascals. Is this statistically correct to do?
Again, the reason we do it was because it proved to be a better way to do it than just doing tests at 10 pascals. That's the reason we do it today. So I'm going to say yes. But again, it's because we've learned over time that this is the most appropriate way is to pull it off the slope of the line as opposed to doing the test at 10 pascals.
So we got one question that says, please clarify. You make reference to exterior air barrier like it's optional. I'm not sure if I'm missing something, but our inspectors check for exterior Tyvek or Typar, and we are also required to use poly if we are not using a flash and bat type of structure.
Interesting. Yeah, that's interesting. I think it's from Robert. So Robert, I probably have a couple of questions to ask you before I would be able to answer that specifically. I'll just simply say that I'm not saying exterior air barriers are optional. I'm saying they are an option. So when you talk about Tyvek and Typar on a home or a building, sometimes we think that it's the air barrier, and it might have some redundant air resisting purposes. But 90% of the time that Tyvek and Typar are installed on the outside of buildings in Canada, it's actually there as the second plane of protection, or what's called the water resistant barrier. And inside, the principal air barrier is applied, which is poly. So what I'm saying is, what we're finding is that if you are able to do the exterior water resistant barrier with the house wrap or with the Codebird air barrier system or these others, and if you apply it correctly to the manufacturer's instructions, because remember, Tyvek and Typar's instructions for using their product as an air barrier are different than for using it as just a water resistant barrier. So if you are using it as an air barrier, then note it on the detail, make that your primary air barrier, and you will not need to have poly on the inside as the air barrier. So I'm not saying air barriers are optional. I'm just saying that you need to define what is what. And what we're seeing in the industry is more and more folks are discovering the opportunities with moving the air barrier plane to the outside. It's synergistic, right? Like if you have a good house wrap, seems to seal right. If you can make it continuous with your ceiling poly and with the foundation at the bottom and with your windows, why wouldn't you want it to be the air barrier? And then you can stop worrying about so many of the other details on the inside.
So to reframe even that same point, so one person has just asked, do you have any issues with having an exterior and an interior air barrier, having two?
Not at all. I know belts and suspenders. My only concern with that is this. Sometimes we don't get the first solution figured out like we should, and we just throw another one at it. So what I would say is, first of all, define your primary air barrier. Because remember, if you're using bits and pieces inside and outside, where's the continuity? And I've seen projects where they've tried poly on the inside and they've done some stuff on the outside, but it's not connected and they still have leakage. So first, define the line that connects all the spots around the home as an air barrier. And then, yeah, if you've got an exterior air barrier and a house wrap in addition to that, great. Or maybe that's all it is, and you just put something on the inside in addition, fine. But define the primary air barrier, that continuous red line first, and then put another one in. That makes sense.
For sure. Now I'm going to ask this next question, but I think we might need to get clarification on it. So I'll ask it. And if we need clarification, then that'll give us time while we answer the last question that's listed here. So it's, could you recommend any free airtight calculators?
Let's see. Wow. I would ask, so what kind of calculation? Is it an airtight calculator to calculate the results of a blower door test, for instance, and obtain your inputs for the energy model? Or is it a calculation that takes the results of a blower door test and calculates the approximate energy reduction? So that's what I need to know.
Okay, so if you could, the person that asked that question, if you could just provide some clarification, we'll move on to the next question and then maybe we can come back to that one. So, okay, thank you. So the next, oh, they just popped it in. It says a whole house as a system. So I'm wondering. Oh,
interesting.
Yeah.
Yeah, I'm, Alexei, outside of a energy model like Hot 2000. And again, even a Hot 2000 is simply going to give you the energy output. You can put in the blower door test results. There is an area where you can put in the results at the various pressures and it'll calculate it for you too. But it gives you the energy output. It might give you your commensurate carbon reduction a little bit too. It'll give you some cost savings annually for if you have the proper fuel costs. That would be about the closest. I have not seen a calculator though there's all those things and then also identifies the other building science intersections. So how much potential moisture goes into the wall if you plug in the relative humidity of the home and the temperature and the outdoor conditions. Maybe someone come up with that. Anyways.
Okay, well, it looks like we've got one last question, unless any others pop up. Would you consider open joint diagonal board sheathing safer than plywood or OSB in terms of potential as a condensation plane?
So, Jim, I'm going to describe this. I don't know if I have that correct. So when you say open joint diagonal board sheathing safer than plywood or OSB, are you talking about, for instance, rather than having full sheets of OSB or plywood, you actually would have a diagonal, like an inlet or a board that would enable the wall to, like you could frame it up, you'd put the diagonal structural piece on, it would keep the wall from racking, it would provide reinforcement. And then the idea is you wouldn't have that condensing plane on the back of the plywood or OSB. Is that what you're asking?
Let's see if he responds. I'm almost wondering, or is it something, just wondering if it's something to do with, like, say, an older home.
Could be.
Yeah. And so where, you have gaps that can allow it to.
So here's the thing just to remember is that it could, from the studies that we've seen, even for instance, the Coquitlam test hut that was done several years ago now down in BC, is that any materials, whether they cover the entire wall or not on the outside, if they're cold, there is a propensity for condensation to occur on the backside. So even there might be other open spaces. I know, and I've seen, walls built where they'll cut a hole in the OSB at the bottom and holes in the top, hoping that it allows the wall to dry out or somehow perpetuates added vapor diffusion to the outside, and it doesn't seem to work. So again, the thing to do is make it airtight. And if you're going to have OSB and plywood on the outside, that's fine, or fiberboard, whatever. But the next thing to do, other than making it airtight and making you shed water, is to add some insulation on the outside and make those solid surface members warmer. So
yeah, he just mentioned that, yeah, he was referring to an older home, like how you used to see in the older homes.
Yeah.
So
that's a good question, Jim. I don't know if I can actually answer that directly. I just know that it's you probably still are going to have a little chance of condensation on some of those members, especially if you add insulation in that cavity. You make them colder, you don't do anything about the airtightness. So I would say in that scenario, whether it's OSB or cross members, whatever, just make sure you make it good and airtight in that old home renovation you're doing, and manage the rain, and you should be okay. And if you have a chance, put some insulation on the outside, sort of in those priorities. Manage the rain, make it airtight, and then put insulation on the outside if you can.
Now, if you already have the siding off to manage the rain,
there you go.
And you put your insulation on. Hey, that's right. A renovator thinking.
Right. Again, just to note, it's very interesting. I remember Joe Stebreck. Joe is Oriole Joe's great building science, though, but he always says, like he says, it's the stuff that gets wet is always the cold stuff, and we have to remember that. If we can keep things warm in the structural wall, whether it's the sheathing or the framing members, that's a good thing. And the only way we really can do that isn't by putting more insulation in the cavity more and more. It's about getting it on the outside, to Stephanie's point.
Actually, one of the questions got lost in the chat, and I just came across it for Robert. Do you have an example or diagram of a well-sealed rim joist cavity, specifically the vapor poly detail? But even to that point, yes. The insulation on the outside is also a really nice detail on that too.
We do have some details that we could share. Actually, Steph, we do. So if you want to send Steph an email, we'd be glad to share some of those things. Steph, I don't want to inundate you with emails, but Steph and team do have some details that we use. Again, they're not stamped details, but some of them are isometric, so they're easy for the field teams to understand, because a lot of us are more visual than we are to understand plan view. So yeah, send us an email. We'll share what we have with you for sure.
Yeah, absolutely. And in fact, Andy, maybe what we can do is send that out in the resource email.
Absolutely.
As well. Yeah. All right. Okay. Well, I think that wraps up all of the questions that we have. So thank you, everybody, for joining us. We really appreciate that. And of course, I just want to remind you, let me just see, I'll go back to my slides here. Just, of course, we want to thank Enbridge for their continued sponsorship and support of the industry in these educational programs. Just a reminder about the fourth in our 4-part series on the carbon topic. And that will be next week. And then in December, Gord and I will be hosting the last webinar for the year. And just so that you know, we will be continuing the series in the new year. So we're really excited to yes.
And that session you're doing Ring in the New Year, that's on new home sales?
Yes.
How to sell high performance homes?
Yeah, it absolutely does. And of course, I always, as a renovator, I'm always kind of thinking through that perspective too. So some of these things are certainly transferable in renovation, but absolutely, yeah, it's how do we sell this high performance? Because the reality is, that's where we're heading, just like you showed with the code. So thank you, everybody, for joining us. The resource email will be sent out afterward, but all of the resources for all of our webinars are available on our website about a week or so after the event. So you can certainly capture that there as well. So thank you. Have a great day, and we'll see you next time. Bye.
Alrighty. Take care.